So today we're going to be going over the free body diagrams on a flat and slanted surface. First, we're going to be going over the flat surface. We have forces going in the y direction, also known as normal force and gravity. The way to find force of gravity is multiplying 9.8 meters per second squared times the mass of the object. And the force going in the opposing direction is normal force, which is perpendicular to the surface. The next forces we're going to talk about is the forces going in the x direction, also known as the force of action, which could be a push or a pull, and the force going the opposing way, which is friction. Now looking at our coordinate system, y being positive going up and x being positive going to the right, we see that force of action and normal force are both positive, and force of gravity and force of friction are negative. And they cancel each other out if the object is stationary.
So now we're going to talk about a free body diagram for a slanted surface. Now the main difference for a slanted surface versus a flat surface is that our object is now at an angle, and for the forces on our objects, we still have the same force applied and the force of friction in the x direction, and we still have a normal force and a force of gravity. Now for the slanted surface, we have to separate force of gravity into its two components of force of gravity in the x direction and force of gravity in the y direction. And we do that by using the theta, which is down here, and we superimpose the triangle over here, and so we have the same angle for each theta, and the force of gravity in the y direction will equal the normal force. So over here, I'm going to talk about how you find the force of gravity in each component. So force of gravity in the x direction will be the mass times the sine of theta times the force of gravity. Force of gravity in the y direction will be mass times the cosine of theta times force of gravity. And so the force of gravity in the y will equal the normal force. And this is how you solve for a slanted surface.
So I'm going to give you an example of a free body diagram on a flat surface. Now let's say we have a force coming in at an angle, and let's say this force is equal to 20 newtons. In order to find how our box is going to move, first we have to find the vertical and horizontal components. So our vertical component is going to be represented by a downwards arrow, and our horizontal component is going to be represented by an arrow going to the right. Now we can plug in the vertical component, which again is represented also by a downwards arrow, and we found that this is also equal to 10 newtons. Because we added another 10 newtons, for the normal force, it's now going to be 10 newtons plus another 10 newtons. So this arrow would now become a bit longer because it's still counterbalancing the force of gravity and the force of the vertical component pulling it downwards. So now the only force left is the horizontal, which we know is going to the right, and we found that this force is represented by 10 square roots of 3 newtons. So by looking at this free body diagram, we can see that because the normal force still counterbalances the two forces pulling downwards on the box, our box is going to move slightly to the right.
This is a box on a slanted surface, so if it was 100 kg, we would find the force of gravity by doing mass times gravity, which is 100 kg times 9.8 meters per second squared. So our force of gravity is equal to 980 newtons. And then we break up the force of gravity into two components, the FG perpendicular, which is perpendicular to the box, and then FG parallel, which is going parallel against the surface. So FG perpendicular is equal to FG times cosine of 30, which is just trigonometry. And then, so that's 980 newtons times 0.866, which is about 850 newtons, which also happens to be our force or normal force because it's perpendicular to the surface. So that counteracts the balance and makes the object stay there. And then the force of gravity parallel is equal to the force of friction, but we find that by doing Fg times sine of 30, which is 930 newtons times 0.5, and that's equal to 490 newtons. So that's also equal to a force of friction because that's going to counterbalance the force that the force of gravity parallel does.
Which is force of normal force and
So this is a box.
Today we're going to be going over the free body diagram in a flat surface. Wait, stop the time.
Because our object is at an angle, our force of